Okay. Yeah, and the next talk will be by Alberto on lattice-based commitments from commutators. All set, you need the clicker as well.
Thank you.
Okay, I already did the intro, so just go ahead, Alberto.
Thank you very much. Hi, everyone. My name is Alberto. I'm here to present a paper called ABBA, Lattice-Based Commitments from Commutators. This is a joint work with Andrew Mendelsohn, and in particular is a work where the problem SIS, short integer solution problem, meets quaternions. And whether the name ABBA has anything to do with the Swedish band of the 70s will be shortly revealed. Yeah. So the motivation is that, in general, some of these lattice-based constructions, they use some cyclotomic ring, in particular of some conductor n, which is a power of 2. And when that power of 2 is large, then we get these jumps in dimension of the cyclotomic field over Q. And in some cases, we may want to trade off some of that security for compression, because we may have some bits of security that are not needed for our scheme. So with that, that's exactly the motivation for our work. And we find a commitment scheme that compresses the inputs 25%. And we trade some of that security for compactness. So how do we do that? Well, we use something called commutators of quaternion orders modulo Q. And to recall, what a commutator is of some ring is that given two elements, A and B, we get AB minus BA. So hopefully that mystery is solved now. And for non-commutative rings, this element is not 0, but the trace of the commutator is 0. So we have this natural compression from the commutators. And the commutator is a function, in particular a bilinear function, which means that if one entry is fixed, we have a linear homomorphism of the second entry. And that will give us the homomorphicity of the commitment scheme. So some preliminary definitions. We start with a quaternion algebra over a number field. This is the Hamiltonian classical definition of a quaternion algebra. In our case, A and B are -1 for both cases. And what's important here is that this particular algebra is non-commutative. Now, for our constructions, we use an alternative definition based on cyclic algebras of dimension 2. And there's always going to be a field, L, such that the field extension L over K is of degree 2. And we also have a degree and field extension of A over L of degree 2. And K is going to be totally real. L is imaginary. So by fixing some automorphism of this Galois group, we have some such algebra called A as well, which is our way of defining a quaternion algebra with cyclic algebras of dimension 2. And these two definitions are equivalent, but we use the second one for our proofs and constructions and so on, because ideals and orders are easily defined, naturally defined in this cyclic algebra. So the main object of our work is this natural order, which is the simplest order that we get from this algebra, which is taking two copies of this ring of integers of L and sum them together. To wrap our minds around the particular objects that we are working with, as we say, we work with cyclotomic fields of degree of conductor 2 to the power of some number, which we call n. K is going to be our totally real subfield. And again, we have our ring of integers, OL and OK. And the algebra is the cyclic algebra that we defined earlier. Briefly, a lattice is a set of random linear combinations of some basis vectors. And we generally based our lattice problems with these worst-case lattice problems. So that gives us our hardness assumptions. And in particular, we have the closest vector problem, which is that giving a lattice L and some target T, we want to find the closest non-vector lattice point to this target T. And if this target T is the origin, then we have the SVP, or shortest vector problem. The SIVP, short independent vector problem, is finding some n short linear independent vectors for some n rank n lattice. So that's the worst case hard problems that we have for lattices. And then for our constructions, we want something called average case hard problems. And in particular, we have these variants of cis. The one I'm defining here is the ring cis. And as we are going to see, we have these different variants that take a different space. In this case, we have the ring, and a different function. In this case, we have the generalized compact knapsack. So basically, given some random A, which is a vector of ring elements, we want to find some short Z such that the inner product of A and Z is equal to 0. And we have the inhomogeneous variant of this, which is that when the target V is not 0. But again, the rest of the definition is the same. So just to compare our construction with something that was widely used, and a bit of history is that in 2002, Mikankyu studied this function called the generalized compact knapsack for some elements in some vector of rings. And that ring in particular is this nice ring that we are going to see something shortly about it. And he wanted to show that this function has nice properties, in particular that the image is uniform, that it is a one-way function, meaning that there is no invertible, it's not invertible, and it's collision resistant. So he was able to show that this function is close to uniform when x is well chosen, meaning that it's short. He was able to show as well that he could find some x of this function such that the function is invertible if x is short. And the way he approached it, and is similar to how we approach as well these problems, is that he wanted to show that this function f is on average as hard to invert as it is to solve this hard worst case problem for lattices called SIVP. So the way we work in these cases, we have this polynomial time reduction from a worst case problem to an average problem, in this case SIVP, to homogeneous cis. He was not able to show that it was collision resistant, and it is because for that particular ring, it was not collision resistant. So after some years, I think it's 2006, by changing the ring, in this case using a cyclotomic polynomial, he was able to show that this function, the generalized compact knapsack, was also collision resistant. So now we get to our work. We do two simple things. We replace the space. In this case, we replace the ring of integers, or a cyclotomic ring, to our natural order. And we replace the generalized compact knapsack function with our sums of quaternions modulo Q. And again, we want to show the same properties as they showed. We want to show that our function is one-wayness. So if the function is close to uniform, then it means that inverting this function is equal to solving some inhomogeneous commutator cis, which are going to define what it is, but you can have an idea from the previous definition. In this case, we changed our ring with our quaternion algebra, and we change our function lowercase f with our sums of commutators. So for that, we reduce worst-case lattice problems to inhomogeneous com-cis, and that means that this function is a one-way function. For collision-resistant, finding a collision of two different inputs means that if both of them are short, the subtraction of the two is also short. And if we can find such a collision, we can solve commutator Cs. So for that, we also have this reduction from worst case lattice problems, in particular SVP, to COM-Cs. And for that, and with that, we can show that our function is collision resistant. So that's what we do. We study when this function is close to uniform. We show these reductions for both cases. And just to wrap our minds around these problems more concretely, these are just definitions of what I said so far. And you can see the similarities to the original definition of ring Cs. In our case, we, as I said, change the space and change the function. It's important to note that the domain, the range of our function is the traceless elements of our quaternion order. And then we have the two variants in homogeneous when our equation is equal to some, our function is equal to some v not equal to 0. And one important point is that we have a variant of this problem when our entries of A, which is the random elements that we get using some uniform distribution, is restricted to invertible elements. And just for completeness, as you can see, we keep the generalized knapsack function and we change the domain. In this case, we use some quaternion orders. We have some other problem called inhomogeneous Cs in quaternion algebras or IQCs. So now we are ready to show our results. It's nothing new. What I've been saying so far, we can show that this function is uniform for some parameters, taking A from some uniform distribution, X from some discrete Gaussian distribution. We can define our function as we've been saying so far by the sum of commutators. And the range of this function is T0. And we can show that this tuple A and the image of FA is uniformly distributed with high probability. We also show that this is collision resistant. This is the conventional reduction from the approximated SVP for some bound. So we choose an ideal. Q, which is the modular that we use for our field, has to satisfy some properties, in particular being completely split in the totally real subfield and ramified in, and then, by showing this polynomial time reduction, we can show that our function is collision resistant. And lastly, we show that this function is also one-way function, but we say it's partial. So we say that there is a polynomial time reduction from the inhomogeneous quaternion Cs, where the random elements A come from invertible elements, to our inhomogeneous commutator Cs problem. So it means that our problem is as hard as the one that we are reducing it from. So we reduce all the way from SVP to IQCs prime or star. To IQCs, and then we reduce from IQCs to ICOM-Cs. So this is a gap in our proof. We make it holds for some constant m, but when m is linear in the size of n or in n, then we don't have that proof for some technical reasons that I'm happy to talk with. So if someone can solve this thing or can have ideas about how to solve this one, I'll be very happy to talk to. And so we have this function with all these properties, and then now the obvious question is what can we do with it? In particular, we can have a commitment scheme. This is very conventional stuff. We sample some random elements. We want to commit to some short vector by sampling some random element from some discrete Gaussian distribution that is of short norm, and we can compute the commitment, and then we can also open the commitment. In particular, this commitment is hiding because of the property that we showed earlier when R is taken randomly from some discrete Gaussian distribution. Binding, again, we have two different inputs to this commitment. If the output of the commitment is equal, then we have the second equation. And if we can solve the second equation, means that we can solve the commutator Cs. So this function is also, this commitment is also binding. And as we were hinting with the bilinearity of our commutators, we can also show that this function is homomorphic, meaning that the random linear combination of elements, if you commit to that, you get a random linear combination of the commitments of the individual elements. And just to show with apples to apples comparison how we are trading compactness for security here, so we can fix some fields. So in particular, we bring some L prime, which is a bigger field, and the degree of the extension over L is 2. And we can see that the dimension of OL prime over FQ is equal to the dimension of our quaternion order over FQ as well, as a vector space over FQ. And the two functions side by side, they have the same dimension of their inputs. And we can see that our function, capital FA, the sum of commutators, has lower dimension in their codomain. So that shows that this has extra compression, but it comes with a cost. And the cost, as we were hinting all this time, is security. And in particular, we can plug it to something like lithium or MLDSA. And we show that we get lower bits. So for the same inputs, where n is equal 512, we get a different NIST category and less bits of security. And lastly, what can we do with it? Well, we can also show that we can plug it into something like a folding scheme, in particular NEO. NEO has this bit decomposition, so we only need to do additions. And you can see that the additions is mostly the same. I mean, you can see it's almost double because of the subtraction in the commutator. So that adds an extra addition every operation. And the commitment size is, as we were claiming all this time, 25% of extra compression. And again, constructing a one-time signature is direct from this work. A blind signature is also quite straightforward. And for polynomial commitment schemes, which is one of the building blocks for snarks, the commitment size comes mainly, or the proof size comes mainly from the size of these commitments. And I believe that they will be very useful in this context as well. That's all I had today. Thank you very much.
Any questions?
So in this final application where you're trading off security by size, what happens with NEO? Like if you want, let's say, to fix the same level of security, what is the actual gain in size? Is it still 25% or is it less?
Yeah, the thing is, exactly, one important condition is that you are given some parameters, so the initial parameters, and with those parameters, you can get this trade-off, but it comes after fixing them. And if you can see that for your, let's say, your cyclotomic ring that you're using for NEO, you have more bits of security that you may want to need, or you may need or may want, then for that case, you may want to change to something that has compression.
I see. Okay.
More compression. Yeah.
Any other questions?
And this is exactly because of this jump of dimension of these cyclotomic fields that are generally used in these constructions.
So you said that you instantiate like those schemes like NEO or or ABBA with the with this new commitment, but then is the non-commutativity of this quaternion algebra, like, does everything still work, like the sum checks and folding?
Yeah, exactly, because we can also show that it's homomorphic in this sense. So the non-commutativity doesn't mean that the commitment scheme is that has
I was just curious.
Yeah.
I was just curious if you came into any obstacles while operating on this non-commutative ring.
time for one more question, if there's any.
So where does the loss of security come from?
Well, it comes from the fact that the codomain is a space of traceless elements, so it has a hyperplane over the initial order.
Okay, thank you for that talk, Alberto.